All right, so next up, we have Muthu talking to us about ZippyDB. It's a distributed key value store, but the interesting thing here is the unique way in which this service came about and the incremental way the team approached building such a sophisticated service.
Thanks. Thank you. Hello? Hello? You guys hear me? Hi, everyone. Steve said, my name is Muthu. I'm an engineer on Facebook infrastructure working on ZippyDB, Facebook's distributed key value store. So why do we build yet another key value store? So being a part of Facebook infrastructure, I get the opportunity to interact with a variety of application service owners. The point of this being not only to learn from them, not only to educate them on existing infrastructural primitives that they can take advantage of, but to also learn from an infrastructure perspective, what are the missing pieces, what do we need to build so that we can provide them a seamless experience writing and maintaining these services. Now, as part of that, roughly a couple of years ago, we noticed a very common trend. A lot of these application services were using embedded RocksDB for their local node storage solution. So for those of you who don't know what RocksDB is, it's Facebook's effort to build off of LevelDB to get it to handle a variety of challenging workloads. And each of these services had some sort of a custom replication layer that was slapped on top of RocksDB. So a very common ask for infrastructure was, hey, can you build us a generic data replication library so we can embed it and get rid of our one-off implementation? We took a step back and then we asked ourselves, can we offload the data sets associated with this service, these services into one of the existing storage services at Facebook? And the answer was no, for a variety of reasons. Some of these services had fancy time-to-live requirements, so it wasn't just garbage collecting at the key value level, but it was also garbage collecting parts of a value. Some of them took advantage of RocksDB's differential rights, so your value could be a counter, your operation could be bumping it up by one, decrementing it by one, some other fancy counter operation. Or your value could be a list, and your write could be appending to that list, deleting an entry from that list, and so forth. Some of these applications also had a variety of replication topology requirements. So it wasn't as simple as, here's my data set, replicate it to all data centers, or here's my data set, replicate it, but within this data center. It was a little bit more fancy. Put 2 copies in this data center so I get really fast writes, put another copy here so that I get some sort of a data center failover story. And most of these services were write optimized, so heavy volumes of write coming through the system. So for one or more of these reasons, existing storage services were just not an efficient fit. So at that point, we started contemplating about the generic data replication library. And it became clear to us if we just provided a generic library, then application service owners would still need to funnel in replication config, right? So given a machine, what shards does it own? What does the replication topology look like? What does the replication topology look like? If that machine fails, what do I do? Et cetera. So at that point, it became clear to us that we should just build the end-to-end service to provide a more seamless experience for these service owners so that they can completely offload their data sets, become stateless services. And that was the birth of ZippyDB. So while these are the reasons that ZippyDB came into existence, it's evolved into something much more powerful over the last couple of years. And we'll take a look at that over the next few slides. So what is ZippyDB? It's a distributed key value store that's built off of RocksDB. It's reliable. It provides for the option for strongly consistent reads, and there are a few other consistency options that we support. We'll go through that in a bit. It's easily scalable. And when I talk about scalability, I mean not only scaling with respect to constantly changing client workloads, but also operationally super scalable. It's also very versatile. So from being able to support a variety of replication topologies to being able to run on a variety of storage mediums. So here's some core principles that have guided various aspects of our design. So we heavily believe in building any system out using extremely simple blocks. So not only should these blocks be very simple, but the interaction across these blocks should also be super simple. This allows us to build a very strong foundation and layer many, many primitives on top to collectively offer a very rich experience. It should also be operationally simple. So this half-drunk guy should be able to get up in the middle of the night, if he gets paged and keep the system up and running. On a more serious note, as the number of machines we manage increases, we need to be able to operationally scale to them without an increase in engineering resources. Ability to adapt. If you go and talk to any service owner at Facebook and ask them, what is your client workload going to look like 1 to 2 years from now? They won't be able to answer that question. At least not many of them will be able to answer that question. So we needed to build a system that was nimble enough to adapt to constantly changing requirements. This was something that we were very clear on from day one. All we wanted to build was just the data replication library. We wanted to compose ZippyDB using this and pre-existing infrastructural pieces. And we succeeded in doing that. We used RocksDB, we used Thrift, we integrated with the pre-existing shard management service, a pre-existing directory service at Facebook. What this allowed us to do is stay focused on just the replication problem and leverage engineering resources across teams. We also heavily believe in building in small iterations. So whatever we're building, build a very simplistic version of it, put it out there, learn from it, iterate and improve. We'll quickly go through the APIs that ZippyDB offers. A shard is the unit of data management in ZippyDB. So all of these operations are scoped to a shard, unless otherwise mentioned. So being a key value store, we obviously support the basic getting a key, putting a key in a value, deleting a key, prefix-based in-order scans. Grabbing a snapshot of ZippyDB is a super cheap operation. As a result, you can grab a snapshot, using that snapshot handle, perform a variety of reads which will be consistent with each other. We support differential writes, custom compaction filter. So I mentioned that we take a dependency on RocksDB. RocksDB being a log-structured merge store, writes are essentially just appends to a log file. What does this mean? A key can have multiple stale values. How does RocksDB deal with this? Just like any log-structured merge store does, it has a periodic process called compaction that consolidates these values. And RocksDB allows for you to plug into this compaction pipeline, which ends up being a super powerful primitive. For example, the fancy TTL semantics I was talking about can be implemented in this fashion. This is also something we expose via the ZippyDB API. We provide out-of-the-box TTL support at the key value level. Custom write operators, it's a framework for hosting a small piece of the application service logic on the server side, so you can implement atomic read, modify, write primitives. We also have some out-of-the-box read, modify, write primitives, such as test and set, update, and delete. Similar to custom write operators, we also allow for custom read operators. Again, a small piece of application service logic running on the server side. You can perform aggregations without having a lot of data go back and forth on the wire. There's also the ability to do online backup and restoration. So not only is grabbing a backup online, but if you want to restore a subset of your shards in your service, that's an online process as well. Your entire service stays online, including the shards that are being recovered. So I'd only talked about like the vanilla key value storage service API. We also built a few verticals on top of ZippyDB. Now, these are services that have customers in turn. When I say customers, I'm talking about Facebook, internal Facebook customers. We built a counter service. So not only can you do basic counter operations in real time, like increment, decrement, but you can also ask fancy questions like, how many unique users have interacted with X? We built a queue service. So when we shipped ZippyDB, we were very closely watching how customers were making use of ZippyDB, and we realized that a lot of them were implementing reliable queues. So we saw an opportunity. We built a queue and consolidated all these, or looking to consolidate all these one-off implementations. We also built a lock service. So at Facebook, we have Zookeeper for locking. We've been using Zookeeper for locking, but it has limitations on the number of outstanding locks you can have, and as well as the throughput of locking operations. ZippyDB is meant to be a high-throughput locking service, or rather, this lock service is meant to be a high-throughput locking service, and it can support a large number of outstanding locks. So this is a bare bones ZippyDB server. Over the next few slides, we'll talk about the various ZippyDB server components, how they interact with each other, how do they interact with external services. And as we talk about each of these components, I'll keep filling this picture. And towards the end, you'll have a more complete picture. Given that the ZippyDB team's contribution was the data replication layer, most of this will focus on the replication aspect of the system. Data Shuttle, that's what we call our replication layer, is what powers the replication pipeline. We built Data Shuttle as a generic data replication layer, so if at some point in the future, an application service wanted to take a dependency on Data Shuttle, it'll be able to do so. Now, why would an application service do this as opposed to just using ZippyDB? Could be because it has one-off requirements that don't fit into the context of a generic key-value store. Could be because it cannot afford the extra hops to a remote storage service. In the previous picture, you saw that a single ZippyDB server has just one Data Shuttle instance. A given server can manage hundreds of shards at a time, and it's a single Data Shuttle instance that manages replication for all of these shards. Underneath the covers, replication in Data Shuttle is powered by Paxos. How many of you have heard of Paxos? So for those of you who don't know what Paxos is, it's a distributed consensus protocol, which is just a fancy term for a protocol that allows you to come to consensus on a single value in the face of failures. Now, Paxos does not have any limitations on the number of writers you can have for a single data set, but operating with multiple writers means a loss in write throughput. So we run it in a single writer mode, more specifically a least primary mode. And you have a configurable number of secondaries. Typical setup is one primary, two secondaries, but we have other setups as well. All of these roles, primaries, secondaries, they're all assigned on a per shard basis. A given Data Shuttle instance can be primary for 30 shards, and it can be a secondary for 70 shards. And all of this is dynamic. It'll keep constantly changing as machines come up, go down. So as I mentioned, there's one primary per shard. That's the one that handles all the writes. For a write to be considered successful, it needs to be acknowledged by a majority of the nodes. For example, in this case, you have 3 replicas. A write has to be acknowledged by at least 2 of them for it to be considered a success. So as writes come streaming in my fancy animation, the first thing that we do is we optionally batch these writes, and then we stamp a version on these writes. The purpose of the version is to establish a global ordering of all writes on a per shard basis. And this ordering will carry on from the primary to the secondaries. Once we do that, the replication happens in parallel. Now, Paxos requires that all the Paxos messages are stored persistently. So if a node were to go down and come back up, it can continue participating in Paxos in a manner that's consistent with its previous responses to Paxos instances. In Data Shuttle, we persist all Paxos messages to a persistent log that we call the replication log. Replication in Data Shuttle is a simple push-pull hybrid model. What I mean by that is the primary pushes updates to the secondary, but it only waits for a majority of nodes to act. So if 1 out of the 3 nodes is down, it'll wait for 2 of the nodes to acknowledge the write, and it'll keep moving forward. When this node that went down comes back up, because of the versions we've stamped on these writes, it's going to realize that there's a hole. It's going to go talk to a peer, pull the necessary updates, and patch up its replication log. So there's push and there's pull. It's very simple. We talked about writes. As far as reads are concerned, you have a few options. You can read from a primary, in which case you get strongly consistent reads. You can also read from a secondary. If you go to a secondary, you have a couple of consistency options. If you read off of the current state on a secondary, it's not guaranteed to be up to date. You get eventually consistent reads. We also provide a slightly stronger form of consistency, read after write consistency on the secondary, where if a client does a write, we send back the version associated with the write to the client. The next time it does a read, it passes this version in, and the secondary ensures that it does not serve any stale data with respect to that version. Secondaries constantly keep track of their lag to the primary so that if it crosses a configurable threshold, an acceptable threshold, they disable themselves for reads. And all this means is the client will now go retry the read at another secondary or a primary. So I talked about a couple of roles in Data Shuttle, primaries and secondaries. There's also a third role that we support, followers. Now, followers don't form a part of your Paxos quorum. Instead, they asynchronously tail all the messages coming out of your quorum. And they're very useful in many different scenarios. For example, you can use them to establish a hot backup in a remote data center so that you have some sort of a data center failover story. Now, ideally, if you want a data center failover, then you would just replicate your data set across data centers. But what this means is that your client writes are now waiting for cross data center replication, so higher write latencies. If your application cannot tolerate that, then you can use followers to maintain a hot backup and have some sort of a data center failover story. You can also use followers to scale out reads. So if you have a large volume of reads coming into your system, you can add an arbitrarily large number of follower nodes without touching your Paxos quorum to serve these reads. When I say arbitrarily large, I mean thousands of nodes. These followers will form an efficient tree, efficient with respect to bandwidth usage. So imagine these followers are spread across multiple data centers. One or a configurable number of followers will be elected as a leader for that data center. They'll pull in the data once, share locally. And this is recursive at every level, the data center level, the cluster level, at the rack level. There's another very interesting scenario that followers enable. So we've been talking about the Paxos, the replica set being one primary, two secondaries. Now imagine you shrink it to just one primary. What that means is your writes are going to be local node writes, and they're going to be act back immediately. Now hook on a follower to this setup, you get async 2x replication. But there are pros and cons. What do you gain? You only have 2 copies of the data set, not 3. You also have higher availability. What do you lose? There is a chance for data loss. If a write comes into the primary, before it's had a chance to be replicated to the follower, if the primary dies, your write is lost. Also, there's a chance for inconsistencies in the face of failures here. Now, it's not very tough to get this system to be an eventually consistent system, but our initial implementation just leaves the inconsistencies as is. And this is very useful for certain data sets, like machine learning data sets, where it's absolutely fine to have a small amount of data loss and inconsistencies. So we talked about Data Shuttle and how it powers the replication pipeline in ZippyDB. Now that we have the replication pipeline, we need to feed in replication config. What shards does this Data Shuttle instance own? What is the replication topology for these shards, et cetera. For that, we integrated with the pre-existing shard management service at Facebook. Now, given a set of servers, given a set of shards, some requirements with respect to topology, replication factor, et cetera, the shard management service figures out an optimal shard placement plan. And apart from that, it also manages roles. So when it tells Data Shuttle, it owns a specific shard. It also tells Data Shuttle whether it's a primary, secondary, or a follower for that shard. Now, given that it manages roles, it obviously also needs to monitor server liveliness so that if a server dies, it can move over all the primary roles to a different server. If the server remains dead for a long period of time, it'll then move the shard itself so that a third copy can be reconstructed in time. The third thing that the shard management service does for ZippyDB is load balancing. So it periodically runs automated load balancing logic to ensure that resource usage is even across the entire tier. So we embed a shard management client, which basically transparently talks to the shard management service and then pushes all that replication config into Data Shuttle. Now, all of these decisions that the shard management service makes, shard placement, role assignment, et cetera, is published to Facebook's directory service, which is how somebody external to the system can consume it. Now, we talked about how, as writes keep streaming in, the replication log in Data Shuttle keeps building up. Now, obviously, this is an impractical condition to be in. You eventually need to purge these replication logs. You need a more compact representation for them so you can serve reads. That's where the store comes into the picture. You plug in a store into Data Shuttle, and what Data Shuttle essentially does is reads all these writes in the exact same order that was determined on the primary, and applies it to the store. And the version is also persisted in the store so that if the node were to go down, come back up, it knows exactly where to start persisting from. Data Shuttle, being generic, accepts a variety of pluggable stores as long as they implement a very simplistic store API. ZippyDB takes Data Shuttle, plugs in RocksDB. The request handler in ZippyDB is based off of Thrift. As read requests come in, we go directly to the store, read the data, send it back. For write requests, we hand it over to Data Shuttle. Data Shuttle does its replication magic, persists it to the store, and then acts the write. Clients, which are basically application services, embed a fat ZippyDB client, which provides a very simplistic local API that clients can talk to. And underneath the covers, they go talk to Facebook's directory service, figure out if they have to do an operation for a shard, who's the primary for that shard, or who's the secondary for that shard, and they forward the request appropriately. So when I talk about scalability, again, it's both scaling with respect to client workloads as well as operational scalability. It's very easy to add capacity to ZippyDB. Just throw in a whole bunch of servers, automated load balancing will kick in, and even out resource usage across the entire service. Failover handling is also completely automated. Now, for big application services, we maintain separate ZippyDB deployments. For all the small to medium use cases, we have a multi-tenant tier so that we can control the number of parallel deployments we have to manage. Now, with multi-tenancy, there comes a large number of complex problems like resource isolation. The way we solve that is through a really good throttling layer where we throttle on a per shard basis, QPS, network bandwidth usage, disk usage, CPU, memory. We also have a self-serve UI that's built on top of for our counter service and also for our lock service. And now we're building this out for our key value storage service. So what this means is application service owners go to a very simple UI, answer some very simple client-facing questions, and underneath the covers, we basically derive, should this use case be on flash? Should it be on disk? What is the replication topology? What does that look like? And then we provision the shards for these use cases. And all of this happens without any engineering involvement. Smart heuristics for data locality. So as Facebook keeps adding more and more data centers, it's extremely critical for us to be able to scale across these data centers in a very efficient way. Now, given that we're dealing with user data in some form or the other, it's very critical that we also have really fast read and write latencies. Now, traditionally, one of the approaches has been, hey, here's a new data center, let's clone some of the data set and put it in that data center so we have local data center access. Obviously, that does not scale. Now, we did something on a one-off basis for one of our services that we're looking to generalize, which is at a sub-data set level, we essentially try to move the Paxos quorum for that data set closer to the entity that's operating on it. For example, if you're talking about a user data set, move the user's data, the Paxos quorum for the user's data to the closest data center to the user. As the user keeps migrating, keep migrating this quorum around. What does this mean? You still have 3x copies, and you have super fast read and write latencies. So ZippyDB at Facebook. It took us around 8 to 9 months from the time we started building to the time we were able to ship to production. It's undergone some massive adoption at Facebook. We're currently spread out across thousands of servers, serving hundreds of billions of requests a day. And we have some very critical services taking a dependency on us, including various services from Facebook's newsfeed, messaging, and ads. And of course, we are continuously evolving and rapidly growing. So it's the first time we've kind of publicly talked about ZippyDB, and I haven't been able to do any form of justice in 20, 25 minutes. But I hope it was the high-level picture was intriguing. I can take a few questions now. Yes. No, the followers don't, they're not a part of the Paxos quorum. They just asynchronously tail the quorum. You still get, as far as client reads are concerned, they can go to a follower or a secondary, and you get the same set of consistency guarantees. Because we replicate the same versioning that was established on the primary to the followers.
So I have to have some understanding issue with this replication that you're doing. Are you having log
Sorry,
structure?
I'm having a tough time
So
hearing
I have
you.
some questions about the replication that you're doing. If you have a strict consistency, are you doing two-phase commit for every transaction?
Sorry, I'm having a
If
really
you
tough
have
time hearing you.
strict consistency, are you doing some kind of two-phase commit for every replicas in the transaction?
So what we do is so Paxos has, are you familiar with, so the accept and commit phases, right?
Yes.
And we run it in a replicated state machine approach. And writes that go to the primary, like we make sure before we act back to the client, the write is replicated as well as like persisted locally, right? So you have one round trip.
Where does it go? Is there a logging involved here? I don't see anything. I probably
Yeah, so that's the replication log that I was talking about.
that is already there. Okay.
Yes, yeah. So there's a replication log. We persist to it locally, makes it to the store. We act the client request, which is why reads that go to the primary are strongly consistent.
And it goes to any persistent storage like disk or flash, or
I'm sorry, I couldn't.
the logs, do they go to the persistent storage directly, or is
It goes to the persistent storage. And then it depends on the setup. So we have a variety of setups depending on kind of the latency requirements, flash, disk, etc.
Okay.
But it does go to persistent storage.
Hi, just a quick question. How do you do garbage collection of the logs when you have followers?
How do we use garbage collection? So it's usually, this is on a, we cap the logs with respect to total amount of size as well as the amount of time. So a typical node, if it fails, if it's going to come back up, comes back up within like 40 to 45 minutes. So we configure it based off of these parameters. And so if a follower, or a secondary even, right? So if it's down for an extended duration of time, then what that means is when it comes back up, it's not going to be able to fill up the holes on a, just by incrementally catching up, but it'll need like an entire store snapshot transfer essentially to happen. So there's no distributed coordination with respect to like purging the logs. It's a best effort. If you can't incrementally catch up, it's a full snapshot transfer.
Got it, thanks.
So the log service that you have built on top of ZPDB, do you think that that might replace Zookeeper at some point in time at Facebook?
I'm sorry, I'm having a really tough time hearing you.
Would the log service that you have built on top of ZPDB, do you see it replacing Zookeeper at Facebook at some point in time?
That's not the intention, at least currently we don't see it. I mean, ZipDB itself has indirectly, like if you look at like the shard management service that I'm talking about, that internally has a dependency on Zookeeper for some of the state that it manages. So there are some dependencies like that on Zookeeper that we can't get rid of. But
Makes
yeah,
sense.
and so that's, we don't see it being used in that fashion, at least in the short term.
So who are the users of the log service right now? I mean, what kind of services are using them?
Yeah, so you're talking about like Data Shuttle? The log service, right? The log replication service? Yeah, so Data Shuttle is...
Not log, lock.
Oh, lock service. So it's typically applications from that want to do a locking like on a per user basis. So I'll give you an example. If you want to lock a user so that a given user is only active for one survey at a time, so you don't want to bombard them with a number of surveys, large number of surveys, then you would get a per user lock, for example. So the number of locks outstanding can be like a couple of billion, and there's high churn happening on that data set.
So similar kind of applications that would typically use Zookeeper.
So similar type?
The kind of applications that you're using your log service are the same kind of applications that would otherwise have used Zookeeper.
Yes, exactly. Yes,
Okay.
they would have otherwise used Zookeeper, except that Zookeeper doesn't. So it has a limitation on the outstanding number of locks as well as the locking throughput. So it definitely will not scale to this. I mean, unless you can always throw hardware at any problem. So you might be able to get over it, but it's definitely not an efficient solution when it comes to this type of locking. Having said that, Zookeeper has a very rich locking API, like it provides notifications, et cetera, that this locking service doesn't. So they're at different ends of the spectrum in terms of the richness of functionality versus like the throughput and the scalability of these solutions.
Thanks.
Yeah. Yes. So load balancing in the service, so Data Shuttle keeps, and ZipDB server keeps publishing load metrics to the shard management service on a per shard basis. And so there's multiple resources involved. It figures out the hottest resource on the tier, and it load balances based off of that hottest resource. Now, at the same time, so I mentioned there's multiple resources. It also makes sure that as far as the other resources are concerned, we don't violate any capacity requirements. But that's kind of like the higher level idea of how load balancing works. And this is a logic that it keeps running periodically, evaluating the state of the tier and moving shards around.